Welcome to Tutorial 5. Now that we've explored some of the types of archives and proxies that are used to reconstruct past changes in climate, we can start to think more about the tools we can use to analyze and interpret this data. There are multiple reasons for using different types of data analysis tools when looking at paleoclimate records. For example, paleoclimate records sometimes differ in their quantitative climate variable. As we saw in previous tutorials, there are oftentimes many proxies with different climate variables. Therefore, although two measurement types might represent the same climate feature, such as temperature, their quantitative values may be different. For example, one could be delta D or one could be delta 18O. Paleoclimate records can also differ in their time span. Records can range many time intervals in the past. For example, records can be from recent climate over the past 500 years, or can extend back hundreds of thousands of years. Additionally, paleoclimate records can differ in their sampling resolutions. When measuring proxy data, the sampling within a record might not be even, and between records, the resolution may differ as well. For example, a record spanning 1 million years may have one measurement every 6,000 years, whereas a record only spanning 20,000 years may have a sample every 500,000 years. We can use data analysis tools to overcome some of these obstacles in proxy data. And to explore these tools, we'll use 3 randomly generated data sets. Paleoclimate records often have uneven time spacing between consecutive values. For example, in these 3 sample data sets on the left, the yellow data is lower resolution than the blue and red. For certain data analysis tools, it's necessary to put the records on a uniform time axis, both within a single data set and between 2 or more records. And an example of this is shown on the right. Now that we've interpolated the 3 data sets, they all have a data point at each time step. One very useful data analysis tool that requires data sets to be sampled on the same time resolution is principal component analysis. Principal component analysis, or PCA, is a useful tool for analyzing large datasets containing multiple dimensions for observation. This tool allows us to identify a common signal between various paleoclimate records. An example of this is shown with our random data on the left. The original records are shown in the red, blue, and yellow lines in the background, and the resulting principal component is shown in purple. In this simplified example, the common signal is similar to the individual records, but in real paleoclimate records, this can be much more complex. In this tutorial, we'll apply these methods to actual paleoclimate proxy records. The tutorial will also contain some additional details about principal component and other resources that you can refer to understand the background and math behind this approach. In this tutorial, we'll apply various data analysis tools, including resampling and principal component, to records of hydrogen isotopes of leaf waxes, or delta D wax, from marine and lake sediments in tropical Africa. Before we jump into applying the data analysis tools, I want to take a step back and discuss how these proxy records that we'll be looking at report changes in climate. Leaf waxes are the thin waxy coating on the exterior of leaves, and these waxes contain a compound called long chain and alkanes. And these long chain and alkanes are chains of carbon and hydrogen atoms. And because these molecules are made up of carbon and hydrogen, we can measure the hydrogen isotopes of these compounds. In previous tutorials, we looked at delta D of ice cores, and in this case, the delta D was a proxy for temperature. However, now we're looking at delta D of leaf waxes from lake sediment cores, and the lake sediment cores that we'll be looking at are from the tropics. In the tropics, delta D serves as a proxy for the amount of rainfall rather than temperature. So how do measured isotopes of leaf waxes in lakes and the ocean reflect rainfall amount in the tropics? When we start out with ocean water, the isotopic composition is 0 per mil. As we previously talked about, when water evaporates, the lighter isotope preferentially goes into the vapor. Then, when there's an initial instance of precipitation, the heavier isotope preferentially goes into the rainfall. Therefore, we end up with water vapor that's more depleted than the rainfall. As this process continues, more of that heavy isotope is removed from the water vapor during the rainfall events. As a result, the vapor that remains ends up being more depleted because more of that heavy isotope was already removed. This results in rainfall that's more depleted over time because it's coming from an initial vapor source that is more depleted than it originally was. And this process continues, resulting in more depleted rainfall when there's more rainfall occurring. And this isotopic signature of the rainfall gets recorded by the leaves. And we can essentially think of the delta D of the leaf waxes as reflecting the delta D of the precipitation. So overall, what we end up with is when there's a wetter climate and more rainfall, there's a more negative or more depleted delta D precip and delta D wax. In contrast, when there's a drier climate with less rainfall, there's a more positive or more enriched delta D precip and delta D wax. And this process is known as the amount effect and is the primary control on delta D in the tropics. Now that we understand the mechanism for the proxy data sets that we'll be analyzing, we can apply data analysis tools to these records to interpret changes that we observe in the climate.